Hello students, in this video we are going to determine the structure of a given molecule from its MS, IR and NMR data. Okay, so now what is the question? The question, we have been given the mass spectrum, okay, and the IR spectrum, the proton NMR spectrum and the 13C NMR spectrum. Okay, we can see the mass spectrum peaks listed there, okay, and below that is the IR peaks in centimeter inverse wave numbers, okay, and then below that we have got the NMR peaks in the chemical shifts in parts per million, along with the integration of each signal as well as the splitting patterns. And so also for the 13C NMR, where we have the chemical shift, okay, we don't have the integration or splitting patterns for the 13C NMR. Okay, so now we will look at the spectrum one by one, okay, one at a time. First we will look at the mass spectrum. See, the mass spectrum shows an M plus peak at 318. See, that indicates that the molar mass of this molecule is 318, right? Other than that, the other important thing that is we can see here is the M plus 2 and M plus 4 peaks, okay, 318, 320 and 322. They are the ratio of 50 is to 100 to 50, which the M plus 2 peak is the base peak. So, and when does that happen? That happens when the molecule is very likely having two bromine atoms. Okay, so when a molecule has two bromine atoms, then you can get this M plus 2 and M plus 4 peaks in this ratio of 50 to 100 to 50. Okay, so why is that? Because bromine has got two isotopes, naturally occurring isotopes, 79, 81 in roughly 50 to 50 ratio. Okay, so that's why this is happening. Okay, now let's look at the IR. What does the IR tell us? We got a peak at 3020 centimeter inverse, okay, or 3020 centimeter inverse, very likely in aromatic CH stretch. We got a peak at 2985 centimeter inverse, which is an aliphatic sp3 CH stretch, very likely. Okay, we got an interesting doublet at 2850 centimeter inverse and 2750 centimeter inverse. This is very likely in aldehyde CH stretch. Okay, very likely. We also got two carbonyl peaks at 1715 and 1710 centimeter inverse, and both this could be, there could be two aldehydes or two ketones, or it could be a combination of an aldehyde and a ketone. Okay, which the NMR will reveal to us. Okay, and we also see the peaks at 1600 centimeter and 1500 centimeter inverse, which are the aromatic, very likely the aromatic C double bond C stretch. Okay, all right. Why is that? Because we see the aromatic CH stretch here at 320. That's why. Okay, so the compounds seems to have two carbonyl groups from the IR spectrum, that is, and that it is also very likely having an aromatic ring and possibly an sp3 CH atom. Okay, possibly. Okay, CH atoms. Okay, now let's look at the proton NMR. The proton NMR, if you see, there are actually 5 signals: HA, HB, HC, HD and HE. Okay, now the HA is a doublet at 9.8 ppm. Now this is very likely an aldehyde. Okay, because see, the IR has also given us peak suggesting aldehyde or ketone, so very likely this is an aldehyde proton. Okay, it's a doublet, which means there is another proton next to it, minimum at least one proton next to it. That's why it's a doublet, right? So that's what it is. Okay, now HB, if you look, HB and HC, they are aromatic protons. They come in the aromatic region of the proton NMR between 6 and 8 ppm. We got HB, which is a triplet, 1H triplet at 8 ppm, and we have got HC, which is a 2H doublet at 7.6 ppm. Now this can happen only, this kind of splitting can happen only with a symmetrically tri-substituted benzene. There are no other aromatic protons. There are totally only 3 aromatic protons, which means the other 3 parts of the ring are substituted, right? There are substituents there on the ring. So, and this kind of singlet and doublet pattern, okay, for the 3 protons, aromatic protons, can happen only in a symmetrical tri-substituted pattern. Okay, so very likely seems to us that there is a bromine atom on both the ortho position and there is a chain in the position 1. Okay, a side chain. Okay, that we'll see. Okay, now HD is a doublet at 4.4 ppm. So very likely this HD is adjacent to HA, which is also doublet. You see, so they could be mutually splitting each other. Okay, and then we also got a 3H singlet at 2.24 parts per million. Okay, which is very likely an acetyl CH3 proton, right? Acetyl CH3 protons. So what does it tell you? Okay, once again, this is established that there are 2 carbonyl groups here in the molecule. Moreover, look at HD. HD is a benzylic proton. Okay, benzylic proton generally comes around 2.3, 2.4 ppm, but here it's 4.4 ppm because it's also sandwiched between 2 electron withdrawing carbon groups. So that's why it is at 4.4 ppm. Okay, so this is very likely the structure that we have obtained from the proton NMR. Okay, so now let us look at the C13 NMR to confirm this, okay, structure. Okay, so looking at the 13C NMR, once again we can see that for such a molecule we can expect 8 distinct signals. If you look at the structure of this molecule, so exactly we get 8 signals. Okay, CA and CB at 27 ppm and 184 ppm once again indicate 2 carbonyl groups. So very likely one is an aldehyde, one is a ketone, as we have seen from the proton NMR. Then we can see 4 signals in the aromatic region. So this is also consistent with the tri-substituted aromatic ring. Okay, that is symmetrically substituted aromatic ring. So that is consistent with that. We got the CG aliphatic, okay, carbon at 72 ppm. It's a benzylic carbon. As I told you, it's between 2 carbonyl groups, also next to the aromatic ring. So that's why it's coming at 72 ppm. And then of course the acetyl carbon, okay, acetyl CH3 carbon at 28 ppm. Okay, so meaning, so this also once again confirms that there is a second C double bond O, right, in this molecule, right? So putting all this data together, what we can now conclude that, okay, this molecule satisfies the MS as well as the IR data. Okay, whatever structure we have deduced. Okay, if you total the molar mass of the structure comes 318, and we can see that there are also 3 carbonyl groups there. Okay, as indicated by the IR data, you can also see the aromatic ring as well, right? Okay, and also the aliphatic carbon. All those things are satisfied by this molecule. So the conclusion is the given molecule is 2,2,6 dibromophenyl 3-oxobutanol. Now, how did this IUPAC name arise? Look at this structure and see the main chain is indicated in red. Okay, see, so the main chain is an 3-oxobutanol. See, it's an aldehyde with 4 carbons. Okay, with an oxo group in the 3rd position, and there's also a 2,6. Okay, there's also a 2,6 dibromophenyl, okay, substituent in the carbon 2 position. So therefore the given molecule is 2,2,6 dibromophenyl 3-oxobutanol. Thank you very much. Bye.